Hey everyone, let me know if I'm audible. Let me know once if you guys can hear me properly. I can see my screen. Let me know if you guys can audible and visible. Awesome, thank you. Okay, the contest has ended. That's good. Cool. Okay, so how did the contest go? How did the contest go overall? It was quite good. Okay, good. Okay, awesome. Cool. Okay, hard for me. Question two and three were a bit confusing. Okay. Yeah, we'll discuss the questions, right? So let's start with the questions. Uh, One second. Let me just mute my mobile. Okay. Okay, let's start with the questions. So first of all, okay, let's do in a reverse way today, right? So we'll start with the last question and then we'll move up, right? Uh, so let's start with the last question. Again, let's just ignore this one, the code for now. Okay, so the problem statement is Geekland has a very popular real-timing messaging service known as Geekenger. It is similar to other messaging applications in the applications of the world. So and only change is that it deletes the contacts listed at the bottom of the screen if a new contact wants to sneak in. Okay, due to floods in Geekland, all its code bases is lost. Therefore, Geek wants you to redesign it. So again, like this part is not very relevant. Let's come to the actual important part. So implement the Geekenger class, where Geekenger in screen size, constructor of the class Geekenger, the argument is screen size that defines the size of the device of which Geekenger is running. So it will define the device size on which the Geekenger app is running. Send message to a number, receive receive message to a number, and last k messages. This will return the last k messages sent or received. Let's erase this if we can. Okay, I'm unable to erase, but let's see. Okay, and this can be erased as well. Yeah, okay. So last k messages sent or received to a number as a list of strings. When the messages are arranged in order, it is displaying on Geekenger's screen. That is, messages sent or received earlier should come before the messages sent or received later. Okay, again, the problem statement is a bit confusing. So let's actually understand this. And also one more thing, if the count of messages sent or received by a number is less than k, or there exists no contact with the number being numbered, then the return a list consisting of only one string, that is error, right? So if the number of messages that you have is less than k, or if the case is like this, that you do not have the number, like you're waiting for the number for last k messages but you do not have the number at all, so in that case return error. Okay, so that is there. Now you can just send receive last two messages, send last two messages, like that. Okay, so see, first of all, it comes as this number 1 2 3 4 5 6 7 8 9 8. This number sends a hi. Then second message is this number sends a hello. So 2 is the size of the GeeksforGeeks screen, right? So it can hold 2 messages at any point of time. Now 998, this one sends a good morning. So hello is received. Now good morning is sent, which makes it to be the contact at the top of the screen. Good morning is received. Okay, good morning. Okay, now when you are sending or receiving to the same person, just think about how WhatsApp works, right? So let's think about it like this. Let's draw it, right? Okay, so you have, yes, similar to LRU cache, right? So you have the messages. First of all, this is the screen. This is the screen on which the messages will be there. Now the messages will be of the form, only format will be there, right? Only the phone number will be there. So let's say phone number is 1234. Let me take a smaller one, in fact. Yeah. Okay. So this is the screen. Let's draw it again. Let's say this is the screen. So how does WhatsApp work? Think about it. You just have the contact details, right? Let's say the phone number is 1234567898, something like this. So this comes, right? Let's say someone new sends you a message, right? Let's say phone number, some other phone number sends you a message, so that comes at the top then, right? That comes at the top. Now here you do not have the list of messages. You do not have the list of messages in the first screen. You just have the phone numbers. When you click on a phone number, you are taken to a separate screen. There you see the list of messages, right? You see the list of messages like this, that hi, hello. What is the messages from this number, right? Hello, ABC, something like this. You see the list of messages. So in the first screen, this is called, let's call this screen 1. In screen 1, you just see the phone numbers. In screen 2, you see the messages. Okay, you see the list of messages. Now it is said, now a constraint is given to us. We have a screen size. The screen size is for screen 1. The screen size is for screen 1. It will tell you that, hey, given screen 1, you can store at max these many number of elements. At max these many number of elements. And what are the elements? The elements are the phone numbers. Right? So let's consider an example. Let's consider an example. Okay. So see, first of all, one, 1 2 3 4 5 6 7 8 9 8. This phone number sends a hi. Okay. So let's draw our screen as well parallelly. So the phone number, this is our screen. The phone number 1 2 3 4 5 6 7 8 9 8 sends a hi. Message is hi. And also the screen size is 2. The screen size is 2. This is very important. Now the second, again, 1 2 3 4, the same number sends a hello or receives a hello, right? It receives a hello. The second number, the same number receives a hello. So to this number only, hello gets also added. Hello. Okay. Hello is also added. Now coming back, again we have a send. Now the send operation is on a new number, 9989123456. 9989123456, right? So we have a new number and it comes on the top, 9989123456. This number sends some message. What was the message again? The message was good morning. So the message was good morning. Let's write it down here. Good morning. And after that, it also receives another message with same good morning message, right? Good morning. It also receives that message. Just see the next operation. It receives the same message. Good morning. It receives the message. Okay. Now we have the query. Get me the last 3 messages for the number. Oh, sorry. Get me the last messages. Last k messages. This is not 3. This is k. Last k messages for the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, where k is equals to 2. Get me the last two messages. Okay, we are saying get us the last two messages. Now our screen size is 2, right? Our screen size is 2. So definitely the screen, this is screen 1. Screen 1 can definitely hold both the elements. So both the elements will be there. Now we'll check. Is 1, 2, 3, 4, 5, 6, 7, 8, 9, 8 this number within the screen? The answer is what? The answer is yes, we have the number. So now we have to return the first two elements or the last two elements, and in the order they have been sent. So the answer should be hello and hi in this order, because hello comes after hi. Hello has been sent after hi, so hello comes at the top, right? Hello comes at the top, or sorry, at the bottom, whatever, like how it is designed. So okay, no, the output should be hi hello, and that is because why? Let's see the order. Arranged in the order it displaying on the screen, that is messages sent or received earlier should come before. Okay, the messages that are coming earlier, again this is also similar to the WhatsApp, right? This is also similar to WhatsApp. If you think about WhatsApp, how exactly WhatsApp works, the first screen where you have numbers, the latest one comes at the top. The latest one, let's say your friend right now sends you a message, that will come to the top, but the latest message comes at the end. The latest message comes at the end. So similarly here also the latest message will come at the end. So this should be printed only in this order, hi hello. Okay, this part is there. Now okay, this part is okay, I think. So right now we have two numbers, right? We have two numbers. Let's say the screen is divided like this, and we have 9, 8 on top, because that is the latest one. 9, 8, 9, 8, 7, 6, 1, 2, 3, 4, 5, 6, whatever the number was, and we have 1, 2, 3, 4, 5, 6, 7, 8, and here we have hi hello in this order, and here we have good morning. Let's write it GM and GM, good morning, right? Okay, now we have printed hi hello. The next operation is we have a new number on which we have a send request, which is 3344556667. 3344556667. So we have a new number now, 3344556667. What will happen? The screen size is 2. Just think about what happens with WhatsApp. You have the screen, the first screen, it is completely full, and let's say once the screen is full, you cannot scroll down. Right now you can scroll down and get the messages, but let's say you cannot scroll down. So the first screen is full. Which one will go away? The last element. The last element will go away. What is the last element here? This one. So this one goes away, this one goes away, this one comes at the front. Okay, so it changes to something like this, that after this operation, this will become the second one, this will go away, right? So we have 9, 8, 7, 6, 1, 2, 3, 4, and 3, 3, 4, 4, 5, 5, 6, 6, 7, and this hi hello goes away, and this has a message, like this now has a message of good morning, and this has some other message, right? We haven't checked that, but yeah, this has some other message. So this has good morning and good morning. 1, 2, 3, 4, 5, 6, 7, 8, that number is gone because it doesn't fit in the screen. The last one will be gone. Okay, now and it says how are you, and after that you have a query for this last one message for this. So in that case you should return error, right? Because if you see the screen, in the screen you do not have 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, right? So that's why you should throw a error. Okay, the examples are a bit big, so let's actually make it a bit concise and work around it, right? So let's say we have phone numbers defined like this, that phone number 1, phone number 2, phone number 3, phone number 4. Okay, let's say our screen size is 3. Our screen size is 3. So that means it can hold 3 phone numbers, 1, 2, 3. Okay, first of all, let's say we have an operation that we have a send on phone number 1, the value is a. So 1 comes here and the value is a. Rather, one comes at the top of the screen, but again, nothing is at the bottom, so we'll keep it at the bottom because the next element will again come at the bottom. Now, let's say receive, we receive a message for phone number 2 with the message B. So for 2, we will write down as B. Now, this is very important. Let's say we again get a receive for phone number 1 with C. What happens? We get a receive for phone number 1 with some input message. What exactly happens? Just think about WhatsApp. You have the contact, you have your first friend here, you have your second friend here, and like that. Now, let's say your second friend messages you, it comes to the top. It will come to the top, right? So exactly that's what happens here as well. Let me do this. Okay, so this is exactly what happens. So this gets replaced. Let's erase this part as well. 2 is getting replaced, 1 is getting replaced, B comes here, A comes here. Okay, A comes here, sorry, A comes here, B comes here, 1 comes here, 2 comes here, and C, it comes here, right? C comes here, because the messages will be in that order only. Like let's say the first message you received was A, the second message you received was C, so it will appear in this order only in the chat. So it comes up here, right? Let's say after this we have send from phone number 3 with the message of D. So from phone number 3, it comes at the top now. We'll send a message D. Now let's say we have a receive or we have a send event for phone number 4 with the message B, or with some message, right? Hello. Send from phone number 4 with the message hello. So we have a screen size of 3. Which one will get removed? We have a screen size of 3. Which one will get removed? When 4 comes in, which one will be getting removed? Two will be removed. The element at the bottom will be removed, right? Element at the bottom will get removed. Simple. Remove this one. This also gets removed. Yeah, just remove this one as well a bit. Okay. And this comes at the top now. 4 comes at the top with the message hello, let's say. Okay. So this is exactly how it works, right? Now that's what the question demands. Like, it's a very real life based question where you have two screens. You have two screens, screen 1 and screen 2. In screen 1, you have a screen size fixed that is given to you. You will have the contacts in that order. Like you can have that many number of contacts. Let's say screen size is 3. You can have only 3 contacts. Now, it also follows an order, that is the latest message. Whoever sends the latest or receives the latest message, that will always move up to the top. And whenever our size exceeds 3, our size is 3 and we have to introduce a new number, the lowest one goes away. Same as how current WhatsApp works. Now in screen 2, we will have the messages. Let's say we have selected 4. Now we'll see the messages for it. The messages will be appearing in the order they have been created. Like this one has come first, this one has come second, then third, then fourth, in this order, right? So this will be like time will increase in this direction. Okay. So yeah, so that's the entire idea about how to construct this. Now this is very similar, and someone said it rightly, this is very similar to LRU cache. LRU cache also is implemented similar to this, but let's actually not go into LRU cache. Again, the implementation will be same for LRU cache as well, but let's not go into the implementation of LRU cache. Let's think how we would implement this. So we need for the chat screen, we need a flexibility. Let's say this is phone number 1, this is phone number 2, they are on the screen. So let's say phone number 1 comes before phone number 2, and suddenly phone number 2 receives some messages. So now phone number 2 should come before phone number 1. So phone number 2 should come before phone number 1. So that's why we need a flexibility around them, right? We need a flexibility around these phone numbers. And how do we get that flexibility? Is there a data structure? Basically what I'm saying is there a data structure where you can, without much effort, let's say you already know that this is the element that has to be moved forward. Can you just take this and move it to the front? Is there a data structure that allows you to take an element and just move it to the front, provided you know where that element is? Is there a data structure? Like, let's say there are multiple, like screen size is, let's say 15 or 20 or something, right? So let's say there are many elements, 1, 2, like this in order, K, N. Now you are telling suddenly that K should be moved to the front. Is there a data structure that supports this? Yes, linked list, right? Why? Because if you have a doubly linked list, like like in a more better way, it is a doubly linked list, not a linked list. It's a doubly linked list, right? So in a doubly linked list, let's say you know that this is the node that has to be removed and moved to the front. How can you do that? So let's say before K you have K minus 1, and then you have a K like this, and after that you have a K plus 1. So now K has to be moved to the front. So what do? You first take this out. So the previous, now K minus 1 will directly point to K plus 1. So the previous of K, the previous of K is K minus 1. Its next should be equals to next of K, right? Similarly, previous of K, next of K, that is K plus 1, its previous should be equals to previous of K. So basically it is telling that next of K minus 1 is K plus 1, previous of K plus 1 is K minus 1. And now you can freely move this to the front, right? You can freely move this K to the front. So with doubly linked list, we have this flexibility. Now the only concern for us is, given a phone number, yes. So given a phone number, you can always implement a doubly linked list yourself in Java as well. So that's what we'll do. We'll not use the doubly linked list, the implementation of a double linked list in C++. We'll write the code for linked list ourselves. And that's what you can do with Java as well. Just write it yourself. It's very simple. Now, given a phone number, you have to find exactly where this phone number is in the linked list. Let's say phone number equals to X. You have to know where is X in the linked list. Where is X in the linked list, right? So for that, is there a data structure? Is there a data structure that given X, it will give us the address of X in the linked list? Can it give us the address of X or a reference to X in the linked list? Is there a data structure that can help us there? Given X, give me the address of X. Yes, exactly, hash map. We have hash map, right? So with hash map, we can maintain the address. Right? So given X, we can quickly, using the hash map, we can quickly get where is X in the linked list, and then we can move it forward, backward, right? We can just move that node. Once we get that node, we can always move that node to the front in order of 1 operation. Order of 1, and getting from the hash map will also be order of 1, right? So in order of 1, we can actually update screen 1. We can update screen 1 in order of 1. Now the question is around screen 2. So in screen 2, what exactly happens? So we are maintaining the messages, right? So the messages will be something like this, that the first message comes here. And also one more constraint that is given to us, that is, let's see this. Okay. K is less than 20. K is less than 20, and we have to always get the last K messages. We have to get the latest K messages, right? K is less than 20. So let's say we are inserting, we need a data structure where the messages 1, messages 2, messages 3, messages 4, they are stored like this, right? They are inserted, like the latest messages are inserted from the back. But whenever it exceeds 20, because our K will never exceed 20, so whenever it exceeds 20, the older messages can be removed. So we are inserting at the back, removing from the front. Is there a data structure that can help us insert from the back and remove from the front? We can create our own linked list, or we have a data structure in C++ called DQ. DQ, right? DQ. With Q, we can insert at the front. So insert at the front, it will be like this. Message 1, let's say, comes first. So message 1, then message 2 comes, then message 3 comes. Now message 3 will be removed first. So Q will not work. We have to insert from the back. The latest messages should be at the back. The older messages can be removed from the front. So we need a DQ, not a Q. Make sense? Like, just think about it. Let's say we have a couple of messages. First message is hi, then hello, then how are you, and let's say k is 2, like k will never exceed 2. In that case, how do we insert? Like, if we insert like this, that hi in a queue fashion, hi comes here, then hello, then how are you. Now if we see the size is greater than 2, so if we remove from the front, how are you goes away, which is the latest message, right? So it should not happen. So what we want to do is insert at the back, that is hi, hello, and how are you, and then we clear from the front, that is hi goes away, which is the oldest message. So this goes away. So this is what we want to do. Okay, so we have figured almost everything out. Now it comes to the implementation. So first in, first out. No, we do not need FIFO ordering, right? If you just look into the question, we need a different ordering, that is like first in, first out. Yeah, right, FIFO. First in, first out. So a stack might help as well. Stack is FIFO. Last in, first out. Stack is. So stack will not have. Q is FIFO. Yes. Yes, we need a FIFO. Okay, Q has pushback. Sorry, Q has pushback, right? Q pushes at back, pops at front. So yeah, Q is FIFO. We need FIFO ordering. So Q will also work. My bad. Yeah, Q will also work. So I was thinking about something else. Like, if you have removal from both ends, in that case DQ is what you need. But Q will also work. Yeah, we need FIFO. Yeah, it just says that we need the last k messages sent or received by the number of list, right? So Q will also work. Cool. Now it comes down to the implementation. So we can take a look at the implementation quickly. Okay. So first thing, we define a node. We do not use the doubly linked list. We rather define our own doubly linked list. So this is the doubly linked list node. It has the next and the previous. It has the next and the previous. Here you can use the Q as well. I have used a DQ, but you can use the Q as well. This is the chat, right? For the node, it will store the chat, and this is the number for which it is storing. So first of all, initialize with number, and after that, add a message to the chat. If chat dot size is greater than 20, chat dot pop front. Otherwise, chat dot pushback message. So we insert at the back, remove from the front, as we have discussed. So this is how the node is working, right? A node is working, which is basically a number and its chat. Now coming to the main class, that is Geekenger. Here we have screen size, we have the number of numbers that we have, current number of numbers, we have the head and the tail, right? So first thing that we do is we have the constructor here. So we initialize screen size to screen size. For head and tail, we create two dummy nodes. Again, this is not needed. You can do it like you can maintain properly. If you maintain properly, you do not need a dummy node. But we have added like I've added two dummy nodes just to help with like prevent miscalculations, right? Nothing else. But again, if you can choose to create two dummy nodes and choose not to. So we are basically for head and tail, we are always maintaining two dummy nodes. So the actual numbering starts from the next of head. Actual phone number records start from the next of head, and the number of numbers initially is 0. Now let's say you get a number, you send or receive. In that case, the same thing happens, right? I've called this add message method. Now what exactly happens in add message? We have the node. Now first of all, we see if the number is null, if in the map. So in the map, what is the type of the map? It is string to node start. That is, given a number, it will give you the address where it is in the linked list, right? In the W linked list. So it is string to node start. Given a map, we'll check if it is null. If it is null, that is it is not there in the map. In that case, we'll create a new node. That is, it is a new number. It is not there in the in our screen. It is a new number. So we'll create a new node and we'll add to it the message. After that, we'll add the node to our W linked list and numbers plus plus. So we add it to the, so where do we add it? Add node. We add it to the head, right? So node of previous equals to head, node of next equals to head of next. So just think about it, right? This is simple linked list addition. Node of, like, adding it to the head. So we have a dummy head here. This is head, let's say. Next node is some phone number 1, and you have 2 that is getting added here. So what we will do, previous of 2 will be head, next of head will be 2, 2 of next will be the current head of next, and this previous will be 2. This is what you want to do, right? So that's exactly what we are doing here. Node of previous equals to head, node of next equals to head of next equals to node, node of next of previous equals to node. Okay, now we'll check if the number of numbers is greater than string size. If it is, then we'll remove the oldest one. We'll remove the oldest one, that is, we'll remove from the tail. So pop tail basically does what? Remove the tail node and return it. So it just removes the tail node, which is the oldest number, right? Oldest number in the screen. So it removes that, we get that, and we'll erase that from the, first of all, we'll erase that from the hash map, because next time, let's say the number again pops up, so we can insert it again, right? We can insert it again. So we'll erase it and we'll do number of numbers minus minus. After that, MP of number equals to node. Basically, we are keeping the value stored in the hash map. Otherwise, this is the case when the number is not found in the hash map. That is, it is a new number. Now, if it is an older number, in that case, we'll just find where it is in the hash map and we'll add the message to it, and then we'll move this number to the head, because this is a, just think about it, you received a new message for this chat, for this number, that pops up to your head, right? That moves to the top of the WhatsApp screen. So that's exactly what we'll do. And move to head is also order of 1, right? So move to head is basically remove node. We'll just remove that node and we'll add that node, that will add it to the head, and both remove and add are order of 1 operations. So it will add it to the head. So for both add and receive, we'll do the same thing. For the find k last messages, again it's simple. Now we have all the messages in the DQ, right, or in the queue. So we can just get it. So node, we'll just get the node number and the reference to that node. Now we have access to its chat. If the chat size is less than k or it is null, then in that case we'll give error. Otherwise, we'll go through all the elements in the chat and we'll add them to the answer and return it, like in the order, right? So nothing fancy here. And in the chat, we are maintaining like a length of 20 only, because it is given to us that it will never exceed 20, right? It is given to us. This is given to us that it will never, k will never exceed 20. So that's why we maintain only the 20 messages, right? We do not need to maintain more than that. So I hope this is clear. This is the first question. Again, this is more like implementation, and it is very similar to the LRU cache problem as well. So you can just as the next step, you can try solving LRU cache yourself, right? But yeah, like the same idea, right? Whenever you have a problem where you need to move nodes, like you need to move an element here and there, right? In that case, linked list or a W linked list makes more sense. So yeah, that's the idea. Anyways, let's go to the next problem. Let me know if you have any doubts. Let me know anyone has any doubts. Okay, so here also we'll remove the solution. Okay, so let's look into this problem now. Geek went to buy some chocolates from a nearby shop with k coins in his pocket. He found that the shop contains n chocolates which are arranged in sorted order of their prices. This is very important line. It contains n chocolates, but the chocolates are also ordered in sorted order of their prices, right? It is ordered in sorted order of their prices. Now Geek wants to taste costlier chocolate, so he decided that he will buy the costliest chocolate, of course among the ones he can afford, till there exists at least one type of chocolate he can afford. So what he is deciding is that he has some amount, he has some money with him, and the chocolates are ordered in sorted order of their prices. What he decides is he will always have the costliest chocolate of the ones he can afford, and he will continue doing this operation as long as he can afford at least one chocolate. Right? If he cannot afford a chocolate, then he will stop. So he will always try to have the costliest chocolate. So as you know, Geek is a shy person, and hence he will inquire about the prices of almost 50 times to the shopkeeper. Now your turn. So he's a shy person, so that's why he will inquire only about 50 times. He only has 50 queries. Like, given a chocolate, what is the price of this chocolate? He can only question 50 times. Your task is to find the number of chocolates he has enjoyed. So you have to tell how many chocolates he has enjoyed. Okay. And n is the 10 to the power 5. So basically we just have 50 moves with us. We just have 50 moves. We have 10 to the power 5 chocolates, but we can only ask the chocolate prices of 50 chocolates. And in 50 chocolates we have to determine what is the total number of chocolates he can have. Okay, so that is the question. Okay, so 3 5 2 4 6, for example, here we can ask to all the chocolates, right? So again, what it tells here is that you have to restrict your moves, right? So you have to restrict your moves by 50. Okay, so whenever you have a rule of thumb is that whenever you have a question where you have to simulate something like this, right? That within, and also the constraint is very less, like within 50 moves you have to do it, or within 10 moves you have to, within 20 moves you have to do it, right? Like that, then definitely binary search is your answer. So again, what the question tells is that there is a shop. Okay, let's rub this part. There is a shop. The shop has 10 to the power 5 chocolates approximately. Now in a query, what is the name of the person? I forgot. Is it Geek? Yeah, Geek. So what can a geek do? In a query, geek can give a question like, what is the price? What is the price of chocolate I? He can place questions like this: what is the price of chocolate I? And he can ask at max 50 times. At max 50 times. So basically, you have 10 to the power 5 chocolate. He cannot know the price of all the chocolates. He has to do it optimally, and in that way, he has to eat the chocolate. And the condition is that he will always try to eat the costliest chocolate. He will always try to eat the costliest affordable chocolate. Costliest affordable chocolate. Right? So for example, let's say he has 10 rupees left and the chocolate prices are 2, 5 and 15. Which one can he have? He can have 5 rupee 5 chocolate. He cannot have 15. Although 15 is the costliest, he cannot afford that. So what is the costliest chocolate he can afford? He will have that always, right? He will prefer having that. So that's the question. Okay, how do we solve this? Again, big hint, we have to reduce to 50 moves. So it points us towards, whenever we have questions where you have to simulate like this, that you will ask a question and you will have to figure out something by asking questions, and you can ask a question only a certain number of times, like 10, 20 times, 50 times. It hints towards the binary search. It hints towards a binary search solution. Now, how will binary search solution work? Let's see. We have the sorted list of chocolate. We do not know this list, right? We do not know this list. We have this sorted list of chocolates. Let's say at any point we choose this. Geek chooses this index. Let's call this index mid, and we'll know that okay, this chocolate price is 20 rupees, and Geek has 50 rupees. Let's say. So definitely he can have this chocolate. He can have this chocolate. So the costliest chocolate that he can have right now lies on the right hand side. The costliest chocolate that he can have right now lies on the right hand side. Definitely he can have all these chocolates because this is sorted and here we have 20 which is less than 50. So he can have all these chocolates. The costliest chocolate he can have lies on the right hand side. Okay. Similarly, let's say at any point this is the mid and he queries, let's say this has 60 and he has 50, so this means he cannot have this, right? So he cannot have any of the next chocolates. The answer, the costliest chocolate he can have lies on the left hand side. So at every iteration we can actually give out half of the array. We can actually give out half of the array. Okay, so that's there. Now how will we do it? So basically, let's say we get this 20, right? This is the mid, and at mid we have 20, we have cost total price left to be 50. So we find that 20 is the maximum because after that, let's say we have 60, right? So 20 is the maximum we can have right now. In the next steps he can only have chocolate from the left part only. So we can always restrict our movement on the left part after every iteration. Okay, that's one point. Second is, once he has 20, how many he will always prefer having 20 as long as he can afford it. So how many times he can afford it, that can be given by 50 divided by 20. So 2 times he can afford 20 rupees chocolate, that is, it gives 40. What is the amount he has left after that? That is given by 50 modulo 20. That is, he will be having 10 rupees after that. 10 rupees after that. Right? So after he has 10 rupees, now he will search on this space, right? The remaining space, that is this space. He will again search for 10 rupees. Like, what is the maximum he can have with 10 rupees? And this search continues like this. So that is the entire idea. And as we are doing binary search, our movement, our total number of moves also becomes like within 50, definitely within 50. Right, so because we are doing binary search on an array multiple times, so every time at max it can go 20 iterations. So how many iterations we can have? Like maybe 2 3 iterations. So yeah, total will have around 50, within 50, right? So that's the idea. Again, I cannot prove that right now why it is 50, but yeah, it will definitely be within 50, right? So now, like, it makes sense. Like now it is actually done. We can go into the implementation directly, but yeah, like, let's work on some pseudocode. So it's like something like this, that while, first of all, we'll have while maybe k is greater than 0 or something like that, right? While 1, let's say, right? While 1 means we'll run an infinite loop, right? So we'll have low and high. Low equals to 0, high equals to n, or something like this. Now what we'll do here is, first of all, we'll always reset low back to 0 for every iteration. Now why do we have while 1 here? Because the inner binary search will be finding the chocolate that we can have now, but after, like, let's say we can have 20 now, but when we have 20 now, we still are left with 10 rupees. So for that, like, for having calculating for this 10 rupees, we will go back to this and again do a binary search, right? So that's why we have a while 1 here. So we'll reset low back to 0. Now while low less than high minus 1, so we'll check that if, so we'll calculate the mid. Can we take an example? Okay, sure. So let's take an example. Let's say we can only do different chocolates with the same price. Wouldn't that cause an issue? No, it doesn't cause an issue in binary search, right? It will never cause an issue with binary search. We are not, yeah, like, we just want the value. We just want the value. We do not care what chocolate he has. If we take the chocolate or look for the next better question. Okay, let's take an example, right? Let's take an example and try to try run on this. So let's say he has 2 here. The price is 5 here, 10 here, 20 here, 30 here, 50 here, 60 here, 70 here. Let's say he has a total price of, he has a total like that amount of maybe, so actually let's remove 50. Yeah, let's remove 50, right? Okay. So he has a total amount of, let's say, 55 maybe, right? 55 or something, or 58. He has a total amount of 58. So in the first iteration, we'll search what is the maximum value chocolate he can have. So we'll start from low, that is 0, and high, that is n. Now what is mid? Mid is, okay, let's write down the indices 0, 1, 2, 3, 4, 5, 6. So mid is what? 6 by 2, that is 3. So index 3 is the mid. Is it, is does, can he have 20? Can he have the chocolate with price 20? Yes, he can. He has 58 rupees. He can have that. So definitely the costliest chocolate he can have now lies on the right hand side. It lies on the right hand side. So basically we just do what? We check if we can have. So check if uh price less than k. That is what we check. Less than equal to k. Okay, it lies on the right hand side. So what we'll do, we'll move the low pointer. We'll move the low pointer to this. Our low moves to this now. Okay, our low will move to this now. Because again, it might happen the next element he cannot have. Let's say he has 33 or 28. He cannot have 30. That's why we move our low to this element and not +1. Because our low will always point to a valid choice of answer. Our low always points to some value that can be answered, right? That he can take. Now if we go to low plus mid +1, we'll lose out on 20. So we'll always keep our low if it is true. If the price is less than equal to k, we'll move our low pointer to that. Okay. Now what is the mid? Mid equals to 6 plus 3 by 2. 9 by 2, that is 4. This is mid. 30. Is 30 less than equal to 58? Yes. So again, it lies on the right hand side. So our low pointer will move. Our low pointer will move again. Our low comes here. Again, we do not move low to +1, because if we move to +1 now, we actually lose, right? We actually lose 30, because 60 we cannot have. That's why we do not move low to mid +1, but we move it to mid. Now what is the mid? Mid equals to 6 plus 4 by 2, that is 5. So this is mid. What is the value at mid? 60. Can he have 60? No, right? So our answer lies on the left hand side. So we'll move our high pointer now. Our high will point to this mid. Okay, so this is basically a technique of binary search, right? This is a technique of binary search. Let's say you have an array. You have an array which is initially true, and after some time it is false. So you want the first occurrence of false or the last occurrence of true. If you think this is also the same thing, we want the first occurrence of true where this array is created like this. If the check price is less than equal to k, so initially it is true, at some point it becomes false. From here it becomes false, right? We want the last occurrence of true. So when you want this last occurrence of true or first occurrence of false, what you do is you run the binary search in a bit different way. That is, you make your low always point to a true. You make your high always point to a false, right? Now if let's say mid is here, in that case mid is true, so your low will point to this one now, because low will always point to a true, high will always point to a false. And where does this end? This will always end here at this position, where low will point to this last true, high will point to this last false or first false, right? It will always end up this, because low always points to a true, high always points to a false. And we can return low or high depending whether we want true or false. Okay, so that's the idea we are following here as well. Let me drop this. Yeah. So now we have come to this situation, right? Our high point, low less than high minus 1. So our low is at true, our high is at false, and we end our loop here. So we know that right now 30 is the maximum chocolate geek can has. So we'll just calculate what is the number of times 30 chocolate he can have. So that will be given by k divided by 30. 58 divided by 30 is 1 time, right? So number of chocolate plus. So chocolate equals to 1. And what is the number of chocolate he has left after this? So it will be modulo 30. So 28 left. Right? 28 left. Right? So now again for 28 we will start our search again. But we are always sure that as we have ended here in the last iteration, now we definitely have less number of chocolates, right? So we can just prune our search a bit. Instead of running this entire search again, we can just get rid of this part. We can just get rid of this right part because it can never be 60-70. From the last iteration we know, right? Our cost right now is definitely lesser. It will not increase because we have taken some chocolate. So it will decrease. So it can never be 60-70, right? So we are left with 28. Let's write it here. Okay. Now we are left with 28 chocolates. 28 chocolates. And again, we'll do the binary search on this part. So low equals to here, high equals to here. Right? And we'll check again whether it is possible or not. Like this. Okay. Does this make sense? Actually, high will be one more, like we'll actually make high 0.260. We'll keep one more element for high to 0.2. Nothing else. So high will not, because 30 can be a possible solution again. Actually not, we have taken 30 as much as we can. So high will be pointing to this actually. We can keep it because 30 cannot be taken again. We have already taken it as much times as we can. So high points to this. And now we do the binary search again, right? So again we do the binary search, like mid is what? 2. So can we take 10? Our previous low will be high for next iteration. Exactly. Our previous low will be high for the next iteration because 30 we have already taken it as many times as we can. We cannot take 30 any more number of times, right? Because we have done what? K modulo low. We have done K modulo value at low, whatever it is, value at low, right? So definitely this is less than the value at low. So we can keep our high next iteration in this position. So again 10 is less, so our answer will be on the right hand side. So we'll move our low to this, right? And again mid will be this 20 is less, we'll move it, and then there will end here, right? 20-30. So 20 is the answer in this iteration. So we'll take it one more number of time and then we'll continue, and like that it continues, right? So yeah, that's the overall idea. Let's quickly take a look at the code. I think that will I think this should be clear now, but yeah, like the code will make more sense. I think it will make more sense right now. So yeah. Okay, so again, the constructor we are also maintaining a cache here. Why is the cache important? So because we have this utility method called ask, right? So given an index, ask what is the value at index. Basically, we are doing the operation here with the shop, right? We are asking shop what is the value at this index. Now, once we have calculated this, we should also cache this because we do not want to calculate, we do not want to ask the shopkeeper again that whether what is the value. That will be a bad use, right? We are asking the same thing again. So we should cache it, and if it is in the cache, we'll return whatever is the value. Otherwise we'll do this, right? And why we are doing here minus minus? Because the actual array in the shop, it is 0 based, but we will follow a 1 based indexing, right? For us, low equals to 0 means is the breaking condition. If low equals to 0, that will be the breaking condition. That means we cannot take any more chocolate, right? So here we'll do the binary search, low equals to 0, high equals to n. Now the first thing that we do here, first thing that we do is what did we tell? We told that we should always ensure that high should be pointing to a false, low is pointing to a true, high is pointing to a false. One case can be that high is also true, right? All the elements are true. In that case, we should get rid of high first, right? We should get rid of high first. So basically, we are taking as many times as we can take the maximum. So high means the maximum chocolate amount, the maximum amount chocolate that is available in the shop. So we are that is basically n, the nth chocolate, which is the maximum. So we are taking high as many times as we can, and we are reducing k as well, right? So now while one high is pointing, now high is definitely pointing to a false. While one low is reset to 0. Now we run the binary search low less than high minus 1. Here we ask mid and we check if it is less than equal to k, that is we can afford it. In that case, low equals to mid, else high equals to mid. Now if low is 0, that means we cannot take the chocolate, we cannot take any chocolate, so we'll break it, and answer plus equals to, otherwise answer plus equals to k by ask of low, that is whatever is the value. Now second time when we do ask of low, it is cached already, right? It is already cached, so we directly return from the cache. So ask of low and k modulo equals to ask of low, right? And yeah, that should be it. And in the next iteration, our high will become basically high is wherever it is, but we can reset high to low. Right? We can reset high to low. That also works because low cannot be the answer again. Does this make sense? Let me know if this makes sense. Why did we take answer plus equals to why did we take answer plus equals to ask of high? Okay, here, because let's say, what did we tell, was our assumption here, that if we have an array like this, true, 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 false, 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 our high should always point to a false, our low should always point to a true. Only then we can end up in a condition like this, right? High will be pointing at this false and low will be pointing at this true. But here, let's say another condition can be like this, that everything is true. True, 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 true. Now in this case, high is also pointing to a true. So our binary search will be breaking, right? It will not work as expected. So for that, we are getting rid of high. Like let's say high is the amount of maximum amount of chocolate. So let's say it is 50 and we can take 60, right? We have amount 60. So we can definitely take 50. So first of all, just take 50 as many times as you can and get rid of it. So now you cannot take 50 anymore, because 50 you can take one time and after that you are left with 10. So you cannot take 50 anymore. So that's why now high will become a false, right? High will become a false. So that's why we are taking first high as many times as we can and then we are getting rid of it. Does this make sense? Yeah. So that is how exactly our binary search is working, right? Otherwise it will not really work. Okay, so okay, let's quickly complete this because I have missed the match and Argentina is already 2 goals ahead, so I'll have to go and watch it. So the first question, again, pretty simple question. We are so okay, so basically pretty simple question that we have to is the caching in ask method necessary? Yes, it is necessary because again, just think, not necessary if you retain the value, if you do not compute it again, but if you look into the code, right, we are again here, we are again calling ask of low, although it is called calculated here already. So we would use a term unnecessarily. So that's why we are just returning this value. You can return it here as well. You can return it here as well, but it makes it makes the code a bit cleaner to return it here in the cache, and so that it is not computed again. And also, let's say in the next iteration, you again come up to a value that is already calculated, so it again goes to the cache. So it prevents unnecessary queries, right? It just reduces unnecessary queries because you only have 50 queries with you, so you have to be a bit careful about the queries you want to make. Okay, so this is pretty simple question. Like it is said that you have to split them into 2 rooms and they will talk to each other only if the starting letter is same. For example, Paras and Priyanshu and Pratik will be talking to each other, so you have to separate them out in the room, and you have to make sure that the number of unfocused employees is minimized, right? So for example, you split it like this, that Paras, Manan, Isha, Ayush, they are in the same room, and Priyanshu, Pratik, Akshay is in the room. So in that case, Priyanshu and Pratik will be talking to each other, but others will be focused. So this is the best possible combination we can come up with. So our output will be two of them are unfocused. So pretty simple actually. What we'll do is we'll maintain the frequency of the starting characters. So f of 26 equals to 0 initially everything, and we'll go through the starting character of each of the strings and we'll do frequency of that character plus plus. Now answer is 0, and if for any of the values frequency of I is greater than 2, so definitely we have to separate them in 2 rooms. Like there will be a, like, if it is equals to 2, we can just separate them into two rooms, right. So for example, Ayush and Akshay, we have just separated them in the two rooms. But for rest, if it is greater than 2, then the answer will be f of I minus 1, because whatever is the remaining part, they will be talking, right. So here, Priyanshu, Pratik and Paras, three were there, so two of them will be talking. Like pigeonhole principle, right. You have two rooms, so if how do you separate them? Like if you have more number of people, so in one place x guys can go, right. So just separate one of them out, and remaining x minus 1 will be going to the same room, and they will be talking, or they will be unfocused. So fi minus 1, answer plus equals to f of I minus 1, and return answer. So pretty simple. Anyone has any doubts with this? Like I think this is very, like, pretty simple, like the easiest problem that you can have. So any doubts on this question? Just maintain the frequency of the starting characters, and if it is greater than 2, answer plus equals to f of I minus 1, right? Because like let's say if you have three people who are talking, or five people, right? You just have two rooms with you. You just have room 1 and room 2. In room 1, you can, if you keep two of them together, they will talk to each other, right? So you have to separate one person out, and other two, three, four, all of them can be kept in room 2, and they will be talking to each other. So pi minus 1 it will be. Can you write it on the second case? Sure, let's do that. It's anyways half time, so let's do that. Priyanshu, Paras, Manan, Isha, Ayush, Akshay. Okay. Priyanshu is P. So we have P is 2 times. P is 2 times. And after that, we have M, M 1 time, E 1 time, A 2 times. M 1 time, E 1 time, A 2 times, right? So what do we do here? Just see the logic. So this is how the frequency will be maintained in the frequency array. So A will be basically we are doing frequency plus plus, right? So frequency of 0, that is A, will be 2. Frequency of A will be 2, then frequency of E will be 1, frequency of M will be 1, frequency of P will be 2. So for all of them, none of them will satisfy this condition, right? Fi greater than 2, because all of them have frequency of 2, not more than 2, within 2, right? So we can just separate them out, like these two P's can be kept in room 1 and room 2. Similarly, A can be kept here, another A can be kept here, remaining M and E can be kept anywhere, right? ME or ME, it can be kept anywhere. So that's why there is no unfocused people. Okay, yeah. So that is the question. I think this makes this clears things. Cool. Yeah, then I'll see you guys in the next class. Or maybe not, I'll not be there in the next class, but someone will. So yeah, take care and Merry Christmas, Happy New Year in advance. And yeah, enjoy the football match. Cool. I'll see you later. Bye.